Oh, Jake, I'm going to interrupt your screen sharing for a second. Okay. All right. Welcome, everybody, to today's Delegate Assembly, which is going to be a DP0.3 overview by two of the people who helped create the DP0.3 simulation. Pedro Bernardinelli and Jake Kurlander are here. Today's assembly is going to be pretty regular setup. We'll have the first hour for the formal presentation, and then we'll go into potential breakout rooms. So go ahead and start thinking about what kind of breakout room you might want to make today if you want to work on something. The main room, as always, will be for general Q&A with Ruben's staff. And then once the presentation and tutorial are over, we will come back and decide on breakout rooms and make them as usual. So before we get started with the talk, just a couple of announcements. The first one is just what's coming up next in our DP0 virtual seminars this week, or next week at this time. It's Stack Club, and then 2 weeks from now we'll have that was me. We'll have a hands-on tutorial about trans-Neptunian objects, TNOs, in DP0.3 by Andres. And as always, if you're a delegate and you're working on stuff and you like to present it in this time slot, anything from 10 to 60 minutes, you can volunteer to present in future assembly just by emailing me. So today's presentation, we're going to have, our hosts have provided a slide deck that they're going to go through to tell you about DP0.3, and then there'll be a bit of a demo with a notebook, and this is something you can watch them go through the notebook, or if you want to do more hands-on style, you can grab a copy. So we're going to want to go to the RSP at data.lsst.cloud and go in the notebook aspect with a medium container, open a terminal, and then git clone this repo, and you'll get the notebook for today's tutorial with this. I'm going to pop that right into the Zoom chat so that you have it. So yes, medium container. And git clone that, and then it'll be this file that you want to open. And you'll be all ready for the tutorial part, which will be in about 30 minutes. So with that, I'm just going to do a quick check for any urgent questions, issues, inabilities to log in. We are watching the Zoom chat all the time. So you can put any issues that you might be having in the Zoom chat. Just pausing for raised hands really quick. Okay, I think we are good to hand this over to Jake and Pedro. Thanks for being here. Yes, I can see your slides.
Okay, wonderful.
Yeah.
Hello, everyone. I'm Jake Kurlander. This is Pedro, and we're going to give an introduction to Data Product 0.3, the simulated solar system dataset available on the Ruben Science platform. DP 0.3 was generated by a large group of people, primarily Pedro and I, but also several others at the University of Washington, at the University of Illinois, Urbana-Champaign, and at the Center for Astrophysics at Harvard. So DP 0.3 is a data set that contains a few different simulated catalogs representing both the first year of LSST operations as well as the full survey. So we've got two different versions of it. There's roughly 1 billion total measurements of solar system objects over this period. And data products are designed to mimic what the real survey, what LSST is actually going to deliver. So we've got a table for solar system objects, MPC orb, which is in a correspondence with solar system objects, and then difference image sources and solar system object sources, solar system sources. So the exact same formats of of data, and they were generated using prototype versions of the nightly solar system processing pipeline. These are entirely detection catalogs. We don't have simulated images with pixel data, but this is all like after PSF measurement and difference imaging. All the simulations are from the 3.0 cadence, so associated with that start date and that 10-year period. And this was generated before 3.2 came out. And all of the data has some slight scatter and error from the truth values, as according to the expected limiting magnitude and astrometric error that we should expect as a function of apparent magnitude of objects from the telescope. We've also performed simulated linking, so to identify solar system objects, instead of running the real in development linking pipeline, which would take a huge amount of compute time, we've simulated linking to exactly match the design goals, which is 95% linking rate, given a set of conditions that we'll talk about later. And this is all contained in the same database system on the Rubin Science platform that'll be used during operations, so you can access it in the way that you'll be able to access Rubin data and get pipelines set up and prepped. So talk a bit about how we generated DP0.3. Started with a set of orbital elements. We'll talk about the populations that are represented in a little bit. Started with a set of heliocentric orbital elements, along with absolute magnitudes and colors for each object. Unfortunately, we only have G, R, I, and Z colors, no U or Y band. We don't expect that to change the science you can do very much, and it doesn't change the number of detections available by that much. Most of the exposures are still there, and well over 2/3. Given these descriptions of objects, we first used Objects in Field, which is a program, survey simulating program developed at the University of Illinois to calculate on-sky positions for each object in each LSST exposure, and then used a program called Survey SimPP, which was developed at Queen's University Belfast, to simulate the actual measurements of these objects by Rubin. So then, we get apparent magnitudes given colors, add in error based on camera position and that sort of thing, and we make much more accurate slices within the camera footprint, considering things like chip gaps and the exact shape and size of the camera. This was done on a program called Survey SimPP that's been updated into a program called Circa, and both of these are open source and publicly available, and we'll talk a bit more about them later. Given the detection catalog, we then simulated the linking of the objects, the identification of moving objects over the course of the survey. Again, we used the design parameters, the goals for the HelioLink pipeline as sort of the truth, so just a 95% probability of discovery for any object given a set of at least 3 tracklets over 15 days. So there are some objects that you could go out into DP0.3 and discover. There are things that are represented a few enough times and didn't make the 1 in 20 cut that are left out there. You can go test other linking algorithms and that sort of thing. Try to clean up some of the extra. And then, as will be calculated in the daily processing pipeline, we've also estimated the absolute magnitudes and phase coefficients for every object. So the truth values are contained in DP0.3, and the fit values are contained. We've used, I think, just a simple HG model here, so we'll see some of those fits later. But the outputs, what's available in DP0.3, is all of the above, everything we've talked about here. So we've got catalogs of every detection, lists of the objects, along with fit, absolute magnitudes, colors, and orbital properties from the detections, as well as truth values, so we can see how well we expect to be able to recover things from LSST alone. Okay, now we've got Circa is the replacement, the upgraded survey simulator designed for LSST, and in particular for making data products like this. It was developed out of Survey SimPP, the program we used to make DP0.3, but it's a lot more powerful and a lot quicker and a lot more general. Circa, given a set of objects defined by a small number of parameters, just an orbit, absolute magnitude, a color, and then you can also now add things like light curves and cometary activity, which is really exciting. It'll simulate Rubin's detections and measurements of these objects, or any telescope's detection and measurements of these objects. It's a very, very general tool, which is very cool. Circa is still being developed. There are a few speed ups and documentation things that are being built out now, but it is a mature software package. It's been tested a whole lot and used for different projects now, and it's available here at GitHub, Dirac Institute's GitHub, easily downloadable and runnable. When we generated DP0.3 using Survey SimPP and Objects in Field, it took more than a year of compute time, which translated into weeks of actual time, to generate the whole catalog, and now it's been done by folks at Queen's University Belfast in less than a day, which is really, really stunning improvement in runtime and in resources. So huge shout out to the Link team, the Link incubator, that totally redid this program and made it very, very fast, very, very general.
Let me just add something here, Jacob.
Yeah.
So the idea is that in principle, if you want to do something with this data set that is not in DP0.3, you can use Circa to do this. So, for example, I want to check if my linking software can recover a distant planet in the solar system, but this is not included in DP0.3. Then you can use Circa to do something like this. So that's one of the main goals of this tool, is for you to not only do statistics with survey simulation, but also to have an idea of what things will look like in the once data starts flowing, basically.
Yeah, and it's you can switch out things other than the populations as well. If you make a new cadence and you want to check that cadence, you could remake DP0.3 with a different cadence or a different telescope or all sorts of different things. It's a very, very powerful tool. All right, now let's get into the simulated linking. Simulated linking was done with a program called Diffie, which stands for Did I Find It? Written by Joachim Moins. It's a piece of Python code that is used for linking surveys to answer two main questions about efficiency. First question is, what should you be able to find given labeled observations, given truth information about a survey, which we have in this simulated case. And given a set of linkages that are found, how well did your linking algorithm perform? So it's really, really great metrics tool on minor planet linking, and we've used it in particular to find every instance of an object being detectable under the LSST design goals for the linking algorithm, which are that 2 observations need to be made of an object on at least 3 unique nights within a 15-day window. So if 3 tracklets of an object are present within 2 weeks, that object is officially detectable, and we're trying to link at least 95% of those. And then tracklets should be separated by at least an arc second, so nothing moving too slowly, or we get those off. And consecutive detections, so 1 tracklet has to lie within 90 minutes, so no super long tracklets. And so given those three parameters, whenever there's an instance of an object meeting those, we gave it just a flat 95% chance of being properly associated with DP 0.3.
So just to add another thing here as well. So this means that for every object that has a bunch of observations, so for example, things that have arcs that are spanning basically the full survey, each time these conditions are met, it means that you have a 95% chance of discovering the object. However, if you have multiple years of data, the object will have multiple chances of basically multiple 95% probability rolls with their dice to make sure that it's detected or not. So in principle, this means that the linking efficiency that we're simulating is much higher than this 95% thing.
Yeah, Melissa?
Yeah, I was wondering these tracklet metrics and the did I find it for DP 0.3, is that very similar, somewhat similar to the metrics that will be used for real data?
These are the same metrics that will be used for real data. Yeah.
Okay, exactly the same.
Yeah.
Any other questions on Diffie and simulated linking? Okay, not seeing any more. Oh, 2 observations in 1 band. That's a good question. I'm not certain. Pedro, do you remember the band-based?
I think it doesn't matter because we're only doing, we only care about astrometry here, not photometry. So in principle, you can use whatever band you want. But under the hood, I'm not sure if this is the way that it is implemented. I think it is, but I have to double check.
Okay.
All right, let me take over a little bit. So for each object that gets discovered, according to these criteria that we're talking about here, we are running basically a preview or better, a prototype of essentially what the survey will do every day. So we are collecting observations for these objects. We are going to do an orbit fit. This actually didn't happen for the DP 0.3 because we didn't have time to implement that. That's fine. We are fitting absolute magnitudes per band. So the idea is because we have objects that are spanning tens of degrees of phase angle, you can just take the mean magnitude or even the mean distance corrected magnitude that have to actually fit as a function of the phase. And this is what we're showing here in this figure. The good news is that we have so many observations for most of these objects that it's actually a very simple process to do this fitting. And we're actually using the HG12 system, not AG as Jake said earlier. We're actually generating them with the AG, but fitting HG12, which it doesn't make that much of a difference. They are in principle representing the same thing, and you can actually get great fits like we're showing here for each one of these objects. And this object is basically a random object that we picked out of the database. It happens to have lots of detection, so it's pretty to see. You can see the curves really well. And I think that Yumi and Christina actually wrote a tutorial doing this using pieces of the code that we've developed. So you can check that if you're curious. And let me talk a little bit about the populations that we have injected into this catalog. So we have a broad range of populations that basically go from things close to the Earth to all the way out in the outer solar system. So we're starting with this thing called S3M, the Pan-Star Synthetic Solar System model. It's a model from 2011 that was derived using basically all observations from Pan-Stars for the entire solar system as they existed back then. So this S3M thing, this includes NEOs, asteroid belts, and lots of its features, includes a bunch of centaurs, and it goes all the way to the Kuiper belt and some transcendental objects. So here is a visualization of the NEOs and the asteroids in S3M. And one important detail about the simulation is that the density of objects actually matches what we expect to see in the survey for the majority of these populations. So here I'm showing something like 4 million asteroids, and this is essentially the order of magnitude that we expect LSST to find. The actual number obviously is going to be different than that, because we don't know everything we need to know about the asteroid belt, but this gives us an idea of what things will look like in a few years. We also did this process called hybridization of the catalog. So the idea is that S3M, it encompasses basically all ranges of absolute magnitudes. So from the largest and therefore brightest objects all the way down to faint things. But especially for asteroids, we essentially have discovered a good number of the bright asteroids. So in other words, one way of thinking about this is that populations are complete or near complete in this bright end regime. So the idea of this hybrid catalog procedure is that we compare what exists in the minor planet center, so basically what observers have discovered over the last few years, with what S3M says that things should be, and we remove every S3M object that is essentially very close to a real solar system source. And if there is nothing in S3M that matches something we see that in real life, basically, then we add this object in just to make sure that we're not missing any types of objects that may be weird and not very well statistically characterized. So if you look at the histogram here, basically you can see that you have a little bit more bright objects towards the low absolute magnitude regime. That's basically the dwarf planets in the Kuiper belt. But these things have been discovered, so we know that we're not going to discover new ones, or at least we don't expect it to be discovering new ones. And after the inner solar system, we can think a little bit about the outer solar system. This figure is actually one of my favorite figures from my entire career. It was done by Andres, and I think the next tutorial is actually going to be how to reproduce this figure. So this figure is showing what the outer solar system looks like in DP0.3. So you can see some of the broad structures we see in the Kuiper belt. We have the scatter disk, so things with low perihelia, and basically a wide range of eccentricities. We have the classical belt, which are between 40 and 50 AU. We have resonant objects piling up where we expect to see them, for example, the 3-2 and 2-1 resonances. And we go all the way down to super high perihelion objects, the detached population, and long period comets. This long period comet population has two different realizations. One of them simulates objects that are 5 AU or closer. The other one simulates objects that are 20 AU or closer. That represents the overwhelming majority of comets that have been ever discovered. And then we also have a couple other different populations. In particular, I think the most interesting one here is the population of interstellar objects. So very quick orbital dynamics intro. If something has eccentricity less than 1, it is bound to the solar system. It has eccentricity more than 1, it is unbound. And that's how we know these things are interstellar. They have E more than 1. And so here you can see that we have things going all the way down to eccentricity of 10. I think I actually had to crop this plot. We have things with eccentricity of 30, which represents very well how we expect to see basically these interstellar objects. One interesting detail and one important detail is that the number of long period comets and ISOs is not normalized. So this means that there are a lot more objects in there than we actually expect to find. So we have, I don't remember the actual number, it's something like 2,000 ISOs in this catalog. Everyone says that we're going to find 10 with Rubin, so it's obviously a few orders of magnitude of difference here. And there is also an Easter egg. We have a population of spaceships. If you care about technosignatures and things like that, these have orbits that look like both NEOs and ISOs, so near Earth objects and interstellar objects, but they have an extra impulse. So at some point during the survey, they essentially get a kick that is not consistent with their gravitational orbits. And obviously, as you would expect, this number of not interstellar objects, of spaceships is not normalized to what we have seen as well. And then this is actually part of what I'm going to show in the tutorial, but let me go through the slides and talk through what is happening here. One cool thing that we can do with this catalog is we can actually take a look at how will the typical object for any given population look like in the simulation? So first thing, and I guess thing that most of you should care about, or at least thing that I care the most about, is how many observations will the typical object have? And once again, this assumes a cadence, and it also assumes no U and Y meant. But if you care about doing precision photometry of sources and objects, that's what you care about anyway. And so there is an interesting trend going on here where basically the more distant the object is, so the higher its perihelion and the more constant its distance stays as a function of time, the more observations it has. So you can see this basically by looking at the cyan curve. That's where the TNLs are, and they have basically a higher fraction of things with more than 300 observations. And sorry, the other way around. They have a lower fraction of things, higher fraction of things with lots of observations. I know, I got confused here, sorry. Anyway, we have lots of observations for these things. And if you look at the other end of the regime, where you have the ISOs, they have the fewer observations, basically because these are transient objects that come and go all the way out to the outer solar system and get too faint to be ever observed again. This is what we have seen, for example, with Oumuamua. So one other way of seeing this is the next slide. Whenever Jake figures out how to change slides, we can look at the arcs of these objects. So basically, this is the elapsed time between the first and the last detection. And you can see the same structure over again here. Basically, the more distant the object is, the longer its orbital arc. So in other words, the majority of the TNLs have basically 10 years of, will have 10 years of data. And things like the long-period comets and the ISOs, which are these transient populations, they have typically 3 years of data instead. And basically, one way of interpreting this is that there is essentially going to be a constant flux of this transient populations being discovered by the survey, while early on we're going to have a burst where things that have stable orbits like main belt asteroids, Hildas, and other inner solar system populations, all the way down to the Kuiper belt, everything will get discovered early on, and then the survey will just add more observations. So one other way of seeing this is the following plot, where basically this is the date when each object gets discovered. So it's essentially the survival function of the previous histogram. Well, one way of thinking about this. And if you look at the NEO and the LPC curves, they are basically constant as a function of time. But if you look at the other populations, they jump and then get then flatten out. So one extra detail here is that our ISOs have roughly the same time for perihelion passage. So that's why you have basically a year after the survey starts, you have a bunch of discoveries and then it flattens out. That's basically because that's when we chose the time of perihelion for these objects. We can also take a quick look at things like absolute magnitudes. The photometry pipeline that we use here is a prototype, so it's only doing absolute magnitude fits for things with high phase coverage. So basically, we're assuming that things have, I don't remember the actual number, I think it's something like 20 degrees of phase coverage and more than 5 observations. And if you're an outer solar system person, it should become obvious to you that no TNLs will have such high phase coverage. So that's why if you look at the catalog, we actually don't have any absolute magnitudes for any TNLs in there. The problem here is that essentially the solution of the phase curve minimization doesn't get stable if you don't have a wide phase coverage. So don't be disappointed that your favorite population doesn't have absolute magnitudes. In principle, you can go and refit them yourselves, and the numbers will make sense. And here you can see that basically the more distant populations, the more distant one direction here are the Jupiter Trojans, has the widest objects. They are going to something like absolute magnitude of 15, while the NEOs, they're going all the way now to 25. This is expected basically because the absolute magnitude is tells you how bright the object is going to be when it is at its proper distance. And one other thing we can look at is we can look at colors. So if you have good measurements for 2 different bands, you can take a look at its color, quite simply just by taking the difference of the absolute magnitudes. And if we don't do any selection on signal to noise, you're going to see that the colors will look super weird. So this is the upper plot here. You can see basically like a hexagon shaped thing where things have R minus I of -10, which is kind of crazy. We think this is actually coming from a bug in the service simulation software that we had not noticed until like 2 weeks ago or something like that. So don't be surprised if you see something like this. But when we actually do a selection on signal to noise, that is the bottom plot, the things look a little bit more sane. We injected 2 broad color populations, and that's what we're recovering here. I think the numbers make sense. Jake, you're the one that actually set the color, so you can tell me if the numbers make sense.
Yeah, they're good.
All right.
Okay. And to wrap it up, we're going to talk about some known issues in DP0.3. First is that the color classes are pretty crude and pretty simplistic. We only have 2 color classes, and objects within those classes have no variance in colors. It's just a single discrete choice of the photometric distribution. We had V minus R set to 0 instead of what it should have been, about 0.2 for those 2 classes. So overall, pretty much the whole survey is about 0.2 of a magnitude too dim. This corresponds to about a 16% underestimate of the number of objects, at least for the main belt. And these color classes are both color classes from the inner solar system that don't match up well with the known colors of outer solar system objects. And so, you know, the distribution of discoveries across filters and that sort of thing is not appropriate for the outer solar system or the interstellar population. As mentioned before, we don't have U or Y band detections of anything. This overall, we don't expect a large number of U or Y band detections of solar system objects compared to G, R, I, and Z. So this shouldn't change things like the absolute magnitude fits or the number of discovered objects very much, but it is a serious problem in the simulation. And the issue that Pedro just mentioned that's causing these colors of -10 or +10, we believe it's an issue where trailed magnitudes are sometimes overestimated for objects that really shouldn't be discovered, leading to some like 30 magnitude detections getting counted as real. There's a very small number of these. They show up like on a scatter plot, but not on a like 2D histogram. So most of the time it's not a problem, but if you do plot something that shows the whole range of colors, you'll see a few very extreme outliers. And there's lots of easy ways to filter on that, like signal noise and you know, just reasonable cuts there that we unfortunately didn't catch until afterwards. Some of the exposures show a camera footprint that does not look quite like the LSST camera. This is also, we think a survey SimPP thing that is probably fixed in Circa, but we're really looking into it. Again, probably doesn't change the science that much. The shape isn't quite right, but the size is right. So number of detections isn't meaningfully changed. And then the last issue, also just mentioned, is that the interstellar objects all pass by the sun at similar times. So there's sort of a sudden ISO shower that's hitting the solar system and none at other times, which probably doesn't match what's going to happen, but you know, who knows? And they are all absolute magnitude 15, no variance there. So they're all like 7 magnitudes brighter than Oumuamua, which probably isn't right, but who knows? We don't have population statistics on them really yet. So yeah, these are all the known issues. We're working on fixing them and potentially coming up with a better catalog. But for for the foreseeable future, these are just things to work around. Happy to answer questions about them or talk about how we're planning on fixing things, but none of these should fundamentally change except maybe the 0.2 mags thing. Probably none of it changes the top line ideas about the set of objects that are going to be discovered and the kinds of science we can do with Rubin in the solar system. And I think that's it. Happy to take more questions, and if not, we'll move on to the notebook aspect.
Thank you both very much for that presentation. I had a question. This 0.2 mag dim across the board, I don't know if you're familiar with it, but in Yumi and Christina's notebook on the phase curves, they found some discrepancy between the like expected and observed magnitudes. If I remember right, it was on order of this. I was wondering if Christina and Yumi are here, or if you'd already talked about this as maybe being the reason for that.
I have not heard about that, so would love to speak to them about that and work out if that's the same problem. There's a pretty clear signature in the two different color classes that if that is the problem, it will be very easy to identify that is the problem. With what we know now. So yeah. Could you send me a message with their names?
Yeah, we will follow up on that later.
Okay.
For sure.
Great.
Yeah. I
Perfect.
thought maybe you'd already discussed it, but it sounds like no, and that's okay.
Yeah, I talked to you and Christine about this a little bit. It's not exactly the same issue, but it might be related.
I see.
It's still unclear to us what is going on there.
Okay, so you're aware of both things then. Okay.
Yeah.
Good. I also I was making notes, and I think a slide or two back, there was some color plots that went up that didn't look, yeah, it was these ones that have like, they seem to have 7 populations, but I thought there was just 2 colors.
Oh, these top left.
Yeah, what's happening?
Yeah, so there's 2 or 3 failure modes here where one of the colors will be misidentified by about 10 magnitudes.
Right,
and
I just noticed
that's
this.
that's
Okay.
the trailing magnitude thing where you'll have survey SimP people output an object that has a PSF mag of 50 and a PSF mag of like 33 and a trailed mag of 23, and it'll be like 7 AU away, or like something that's just clearly not trailed by a factor of a million or whatever it would be. But it's very rare. It's like I think tens of thousands of detections out of our billion detections or something. It's like a very small population of just very wrong magnitudes that are leading to these fits. There's something cool about the hexagon shape there, where like maybe we could learn something about the failure modes from that, but I don't know.
The hexagon shape is we have 3 bands, and each one of the 3 can fail. So if you fail only one of them, you're going one of the directions. If you fail in 2 of them, you go on the diagonals.
Let's see.
Sorry, to go on the diagonals, you actually have to fail in 2 of them.
Yeah. Okay, that explains it. The plots like caught my eye for a second, and I wanted to go back, and thanks for explaining. Yeah.
The bottom is the cut based on signal to noise. That's what should be. That's what we believe is real, and you see sort of two big clumps there.
Yes.
This red down there, that's probably also a fit failure mode that is not so.
Probably, yeah.
But yeah.
Okay.
Yeah, and one of the details that, as with everything that we're doing here, the numbers are dominated by main belt asteroids. So you can expect to see, basically because there are like 100 times more than any other population, you expect to see more weirdos in there.
But on account of these color issues, even though DP0.3 is distributed well like the real solar system, you shouldn't use these numbers as official LSST prediction numbers. We're working on a paper where we redo this properly with really good colors and really good, everything fixed up, and we should have really good prediction numbers then, given the new cadence and new information. But this is good for testing, but not for official numbers.
The question in the chat, Tom, do you want to unmute and ask it? Maybe a few seconds. Otherwise, I can read it. Oh, hi, Tom.
Yeah. So I just wanted to make sure I'm understanding that same question related to what Melissa was just asking about. So in that top left figure, that orange blip in the middle is actually like a huge mountain coming out of the plot. Is that
Yeah,
right?
That's
It's
right.
like a billion things in that, and then 10,000 spread out in the red blobs.
Yeah, that's exactly right.
And I'll point out, Jake and Pedro too, in the chat, you have a nice congratulations with lots of plus emojis on it for making this simulation. So make sure you read that in the chat.
Thanks,
Thank
Tom,
you.
and everyone else.
I'm just going to pause. I have one more question, but I'm going to pause for other hands. Yeah, I think you're about to maybe cover this last question in your tutorial, but if you go back a couple slides where you had the population, or you just back one. Yeah, even one more. Yeah, here, where you have the various populations. Did you get the populations using the truth data, or did you do some sort of discovery on the observations to classify?
It's a little bit of both. We are using the truth data to determine which object belongs to which population, but we are using the simulation to determine when the object is discovered.
Right. Yeah, but for the classifications, that's coming
Yeah,
from
that's coming from
data.
truth. Yeah.
Yeah, and I think that's not something that is in DP0.3. People
Yeah.
can't. It is?
That's right. No, it's not. It's not.
It's not.
You
Okay.
had to. That's actually one of the things that we're going to do in the demo. You can do a selection like this quite easily on the, basically given the MPC orb table, which is the truth.
Okay.
And
Yes.
one other detail, Jake, can you go back to the previous slide? One other detail related here is that if you fix the distance of an object, the longer the arc, typically the better the orbit fit quality is. So one way to think about this is basically for everything that has more than 8 years or so of data, which is a good chunk of the main belt and the TNOs and etc. Basically, the orbit fits that LSST will get are essentially going to be the truth anyway, because the orbit quality will be so much better than what's typically on the minor planet center that doing anything like this will be trivial.
Oh, okay. Okay, well, with that, let's switch over to the tutorial.
Yeah, okay, I'll stop sharing, and Pedro, can you take over?
Yeah.
Yeah.
We're at quarter to the hour, but I think the tutorial will probably take you maybe 5, 10, 15 minutes longer.
Yeah,
Then
that sounds about right.
Yeah, so I think I'm not gonna stop you. We'll just sort of plan to go past the hour. If people have to leave at the hour, that's fine. If you came here with questions or you're having trouble with anything in the RSP and you were waiting for that breakout room time to ask your question, just send me a direct message in the Zoom chat and I'll try to help you on the side. And then we will still have breakout rooms. We'll just do them 15 minutes later today. So those are your options. You can ask questions now in the chat, or you can wait for 15 minutes past the hour and we'll do general help in breakout rooms. Okay. Thank you, Pedro.
All right, so this tutorial is it's actually quite simple. I'm just going to go through how you can select on these populations and reproduce some of the plots that we showed here. So the usual RSP stuff of importing packages and etc. This query is basically getting the orbital elements for these objects from the MPC orb table. And then it's doing an inner join on the SS object table, which is the one that tells you whether the object has been discovered or not. So there's a flag there. The 2048 flag is essentially, we know this object exists because we put it in there, but it was not discovered. So in other words, if you want to select objects that were linked, you want things that are not, that do not have this flag. And since all the other flags are small numbers anyway, so it's only going to go above 2048 if it actually gets discovered. So let me just wait for the query to finish a little bit. And then we can do some very simplified population splits in the way that we showed here. This is a very gross cut. If you want to do this for real, you probably have to do some orbital dynamics analysis and care about errors and etc. But for the purposes of trying to make these figures, this is totally fine, and we'll get you basically the majority of the objects in the right place. So here are a couple of these definitions, and I'm going through how you can do these things. So one detail is that in the MPC orb table, we do not have the same major axis. We only have the perihelion. These things are easily related to each other. One important detail here is that interstellar objects, they have negative same major axis because they have E more than one. And the problem with using same major axis is that if E is equals to 1, then the same major axis is not defined. So that's why we're doing things this way. So here I'm just doing a very quick dictionary of lambda functions, where if you apply each one of these functions to the catalog, it will tell you what belongs to this population. It's, I don't know, it's just, I like doing things this way. And I think it's easier. And let's see, the query is still running. Let me try to reproduce numbers. Oops, something. Oh, all right. I have never seen that. So let me run this again. Did I do something wrong?
I just got the same error. Let me just
Connection broken. Yeah, I have no idea what this is. Did we crash the database?
maybe.
Did it time out or something? Like the last, it said that the last time you ran it, it said 11 minutes. It's not there anymore.
Can you?
Yeah.
I've never seen a wildcard used in a query before. Yeah, what?
I think this is just taking all the information. Andreas, I actually stole this query from you, so you can help us here.
Oh.
Oh, great.
I edited your TNO notebook query.
No, but then I think I put some, didn't I put some cut or something in ellipticity or something? If you have I don't know if you have the most recent version of the TNO tutorial.
Yeah, I modified that a little bit because I wanted to get all the populations. So yeah, I think it makes sense that it would take longer than yours to run.
Okay.
Anyway,
Can I
I have
ask-
the, sorry, go ahead. Whoever was going to ask something.
Oh, Bob, go ahead.
I was just wondering what the F is for in the last line of the query. At the beginning of the query.
This doesn't need to be here. I think Andres was using an F string basically to
Right.
put
It's
things in the
working now
proper
without
place.
Oh, that's Python 3. That's
Yeah.
called F string. So if
Okay,
you substitute it in a variable, I guess you're not using it here, but yeah, it's if you had a variable of the flag, then you
Mhm.
define it before, and then you substitute it with an F string before the string. That's Python 3 feature. Yeah.
Oh, the good news is that I actually have this this notebook elsewhere, so we can actually look at the values while it's running. And it's almost like I was prepared for this. I wasn't. This simple query, it returns us 4 million and some objects. This is, as we were saying during our presentation, this is basically the order of magnitude what you expect. the real catalogs look like. And so then we can do this splits, and the cool thing you can do, let me just double check. Yeah, I got the same thing again. I don't know. We can figure that out later. Then we can take a quick look at how many objects we have per class. So let me just go through quickly what is going on here. We have the near Earth objects. They're defined with this low perihelion. Main belt asteroids, basically the majority of the asteroid belt. Hildas, things that are a little bit further. Jupiter Trojans, so things that are in resonance with Jupiter. There's a huge population of objects there. We have centaurs, so things that are beyond Jupiter and before Neptune. Transitarian objects, so things that are further than Neptune. You will notice that I have a quick cut on perihelion here. Basically, this is not a physical cut, it's just to avoid the population of long period comets. There are better ways of doing this, but this is a quick and dirty cut. Same thing with the long period comets. I'm basically just flipping the query on the perihelion, and the ISLs are the things with E greater than 1. So you can take a quick look at these numbers here. So I have like 38,000 NEOs, 4 million MBAs. So in other words, MBAs dominate everything we do here. 30,000 Hildas, 80,000 Jupiter Trojans. One important detail is that the number of Jupiter Trojans is heavily dependent on the cadence. So be careful using this number. Meg and the rest of the source system team recently wrote a paper that goes over that into a lot of detail. So take a look at that first. 20,000 centaurs. I am thinking here, I am not sure if the number of centaurs is also normalized in S3N. That's something that just occurred to me. 20,000 TNOs. This is an underestimate. If you remember the numbers that everyone has been quoting for the last 10 years, where we're saying 40,000 TNOs. We think this is very clearly due to, one, a difference in the population model that is being used, and two, the color offset that Jake was talking about. 3,000 long period comets and 2,000 ISOs and 100 spaceships. The spaceships will not turn up in this query because they are hidden in the catalog. So you actually have to try to find them. There is a shortcut. The spaceships are the only ones that actually have U and Y band observations because they use two different people that are processing. So if you want to cheat and find your spaceships very easily, that's one way. The other way is that I think they have, if you look at their names, I don't remember the actual name of the column. I think it might be actually named. Their names start with ET something, so that's also easy to find in the catalog. And so we can then, so basically what I'm doing here is I'm constructing smaller tables with each one of these populations, so you can take a look at things like the plots that I was showing, the number of observations, and a couple other things. So this is very easy to do if the query actually works on the database. And yeah, so as we were saying, these things are quite well representative of what we expect to see. A high fraction of TNLs will have 500 observations, which is great, and it's you know, if you care about doing photometry for these things, it's a treasure trove of data. So here, I'm just doing the mean, median, and min and max number of observations per population class. There are a few interesting things that pop up. So my favorite one is this one here. We have one TNO that has 12,000 observations. We think the reason is that this object happened to fall in one of the deep drilling fields and stay there for a while. So that's why you can get something like this. And you can see this happening with the other populations as well. We have even an NEO with more than 1,000 observations and a centaur with 7,000. So if you're not a source expert, the way of thinking about this is that the more distant the object is, the slower it moves in the sky. So if it happens to be in a high cadence field, the more distant object will stay there for a while. So that's how you can get something like this out of the data. I was talking about this idea of doing the absolute magnitude fits and etc. Here I'm showing you how to actually get those from the data. There's this band and data column. This means how many observations were used to fit the absolute magnitude in each individual band. And that's why if you look at TNOs and a couple other things, it's basically 0. That's because we don't have a lot of phase coverage for this population. So we're not doing an absolute magnitude fit. But if you look at the main belt, the median main belt object has 50 observations in R band being used to fit its magnitude. So you can expect that the absolute magnitude will be fit perfectly for all of these objects. In real life, these things will have a lie curve, and so you have to actually be a little bit more careful than that. But in practice, you can get a good absolute magnitude for everything. And then you can look at these things such as the arcs. Everything is in there. You don't have to do any further computations. Then I think these are quite useful plots to basically to figure out what's going on. And so, Melissa, to answer your question about the discovery dates, it's this discovery submission date column from the, I think it's the SSO table that we're using here. So you have your spike early on in the survey for basically all populations, except for the NELs and the LPCs that basically have a constant flux as the survey progresses. And let's see. Same thing with the absolute magnitudes. It's all calculated in there. We also have the phase coefficients that I did not take a look here because I had forgotten that we had that problem. But thanks for reminding me, Melissa. That's something that we have to take a look at. And then the color stuff we were talking about, let me just scroll down a little bit and show you how this color figure modes happen. So this is one object that we found in there. I think it's a main belter. Looking at the distances, I'm pretty sure it's a main belter. But if you look at its magnitude measurements, we have some very weird things here where, for example, there's this magnitude 34 Z-band detection with signal to noise of less than 1. And so that's probably this trailing bug that Jake was talking about, especially because its true magnitude should be closer to 28 plus its color term. So don't be surprised if you see things like this in there. Just be a little bit more careful of using them. And yeah, and if you look, it has absolute magnitude in G is 17, absolute magnitude in R is 37. It's obviously this object doesn't have a G minus R color of -20. It's obviously a problem in somewhere. All right, I am a little bit frustrated that the query didn't work out. I ran it yesterday before the patch and it worked. So I wonder if something changed in the patch or if there is a bug in the query that I haven't noticed.
It seems it took you like 12 minutes or something last time, or maybe you didn't realize. Actually, if you don't put any, if you don't put any constraints in the TNO tutorial, I'm putting a constraint for TNOs. So I'm doing what you're doing here, but in the query. So that narrows it down from millions of objects to tens of thousands.
Yeah.
And I don't know what the size of the container. I don't know if you're running out of memory or something.
Oh, it could be. I think I'm running on a small container. Should I change it to?
That could be. You could give it a try. It would be interesting to think how to maybe do the cuts that you're doing, maybe from the query point of view, or
yeah,
anyhow.
I'm pretty sure that it's doable, in principle, adapting your TNO query to basically
I
do
think-
the things.
Right, right. So we will need to think because Tom is reporting that he already did the experiment on a large container and it crashed after
It
3
crashed
minutes.
there. Oh,
So maybe something else is going on. But it would be worth to think about that. Because I think if you don't put any constraints and if it works, it's like 15 million objects or something. I don't remember. Something like that.
yeah. So it's 15 million objects total. Something like 4 million actually being discovered. So that's the 2048 flag. That's strange. Yeah, I don't know. I'm a bit frustrated about this. I got this working yesterday, which is. But you're right. It took like 12 minutes to run.
Yeah, I think, yeah, if it ran yesterday, like before 2 or 3 p.m. Pacific,
Yeah.
then that you're right that there might have been something in the patch that we thought was innocuous, but is causing some subtle trouble.
Yeah, I remember seeing the patch message when I started running it to make this plot.
Yeah, so here we should get the query and the error message just into the forum, and then I can bring it to the attention of our RSP people, and they might just know. I don't have, I could post it, but I'm trying different things, so I'm waiting for the error message to come back.
Yeah.
And then I can get that into the forum for us, and then maybe we can get a response. I just don't want to copy paste it all. It's nicer to have the error message in the forum where it's like nicely formatted. So I'm gonna put it there. But this looks like a very useful notebook with lots of like useful plotting demos, and especially that selections. That's a really useful, very copy pastable cell that has
Yep.
all of the classifications in it. So yeah, so thanks for that. So yes, round of applause for Pedro there, and we can do some more questions while I try to do some troubleshooting.
I see that Tom asked about NVAs and light curves. No object has any light curves in the simulation. That's basically a feature that didn't exist in the simulation software until a couple weeks ago. My point is that every real object should have a little bit of a light curve. It might be a very low amplitude one, but it's probably going to be there. So in practice, in real life, the fits might not be as good as what we're seeing here, but for the simulated objects, everything will look basically perfect, except for the simulated errors, of course.
Oh, Jeff, you already took it straight to our. Okay, in that case, I don't need to post on the forum. We should post.
Yeah, I thought I'd see if we could get a quick response from anyone.
Yeah, can you put the query here as well? Because that's the first thing they're going to ask is what the query was.
It actually shows in the traceback, so it should be fine.
Is it copy pastable in the traceback?
Not
Oh,
sure.
there it is. That's pretty copy pastable.
It's in there.
Yeah, it's in there. Let me cancel this.
Do you have a question?
Yes. So in DP0.3, we don't have Y and U and Y band. And I understand that it's not affecting much for the solar system object study itself, but in real data we'll have U and Y. And is that any like contaminants rate might be increasing for the the solar system studies if we have extra filters? What would be like potential like impact having U and Y in terms of doing the solar system science?
So for discovery, it doesn't change that much because in practice, these basically all sorts of objects are fainter in U and Y than in the other bands. And so the discovery will still be driven primarily by essentially GR and high. Not even Z-band will affect discovery that much. However, U and Y in real life will allow determinations of absolute magnitudes and colors and all of the problems that this bands bring. I've never used U-band data. I've used a lot of Y-band data in different surveys for source objects, and they typically have very low signal size, and it's very hard to get anything out of. So yeah, to be honest, we'll have to wait and see what it looks like in the survey. Things will look weird, and I recently saw a talk in a conference of someone saying that they measured a TNO to have a U minus R color of 4. So we'll see what these things look like in the once we actually have objects.
Okay, thank you.
On the topic of contamination that you mentioned, I think from what I've been seeing, at least in the HelioLink pipeline, so for linking contamination, there should be very low contamination unless there's really a whole lot more difference image sources than there are in like DP0.2 and that sort of thing. So I think U and Y shouldn't contribute to linkage contamination in meaningful ways, unless things look unexpected.
Mhm. To Jake and Pedro, for the magnitude offset and color offset we saw in while working on the phase curve, that's the notebook 4B. If you have a chance to look at it, so we have some plots to show the shift in the input MPCH versus the recovered HG model H magnitude, and also the color offsets. So yeah, there is a plot in text.
All right, that's tutorial DP0.3.
4B.
4B?
Mm-hmm.
I'm in my tutorial notebooks folder and I only see DP0.3 up to 3.
Notebooks DP0.304 were released to Prod Branch yesterday. So if you're in your own Git cloned version, you'll need to do a fetch. But if you go into the notebooks/tutorial notebooks that gets automatically updated, they'll be there.
Just seeing.
Actually, if you haven't logged out and back in, did they appear in
Oh,
notebooks?
I'll try logging out and logging in.
Yes, that's what it is. Yeah. Yesterday's patch didn't force restart. Okay, well, we have Colin Slater currently working on our technical issue. Any more questions for Pedro or for Jake? Oh, cool. Okay. Bob's in Hawaii. That's nice. Wonderful. Okay, so from here, Tom, I think you're our only delegate right now, kind of surrounded by staff and Pedro and Jake. So Tom, if you have any more questions or there's anything that you want to work on here with us, you're our one delegate. So you
No,
you
I'm
get-
good. But thanks, everyone. This is really interesting and very impressive work.
This is great. Thanks, Tom. Thanks for being here.
Sure. Bye.
Yeah, bye. Okay, and Pedro and Jake, thank you so much for this presentation. This was very useful. I have a bunch of notes. There's things I want to update in our documentation. So you'll be getting, I'm going to have you sort of review the updates that I want to make. Just small little things. You have that great list of known issues. I want to make sure that gets into the docs. Can we get a link to your slide deck or a copy of your slides?
Yeah, I can send it to you.
Okay.
Actually, I'm gonna post it on chat.
Are they Google Slides?
Yeah.
Yeah, sweet. And is it okay that I post them in
Yep.
our summary? Okay.
Just make